actually, it's probably the end of the list.
9th, 10th, 11th. Oh my gosh. Okay, yes, 11th. No points for you. Okay, which, a quick rundown of due dates. All of your expert TAs are due this Friday. I'm downloading them on Saturday. If you don't have the work done by then, it's too late. You have a quiz over this electromagnetic chapter due Sunday night. Your final slides for the presentation projects are due Friday night. On Tuesday, you have the option of showing up to class at 2:45 or recording your presentation and posting it to the forum on iLearn. But you need to have your presentation then. If you do the forum, you have to also reply to 2 other people, watch their videos and reply to 2 other people. So you're either presenting in class or you're doing the forum. One or the other is fine.
If you're in person, you also have to.
Nah. So yeah, if you're in person, once you present, you're done. Except for the reflection essay, which will be due next week on Friday the 16th. What you liked, what you didn't like, what you would change. Okay, that's everything. Questions?
So with the video, if we do it on phone, are we supposed to do it on YouTube link or an actual?
Whichever. I always like the YouTube links because they work and embedding mostly works. Yeah, I'm just saying like works versus mostly work. Yeah, just make sure. I would have like a friend log on to it if you do anything and just see if it works for them.
Well, most of the time, people expect YouTube.
Yeah, I think most people use YouTube or some other or Google, their Google Drive, or they just send a share link from that. Do make sure that it's set to be shared. So if you use a link, you have to set it for anyone can open. Okay, any other questions, concerns? Okay, I don't think
5 to 8 minutes.
5. Yeah, not 5 to 8 minutes. It's 5 minutes.
5 minutes.
Don't go under 3 minutes. You'll have points taken off for under 3 minutes. I would request that you don't go over 7 minutes, but I won't take points off if you decide to just talk and talk and talk.
So 5 is equal to middle.
Yeah.
7 is to 5.
5. Aim for 5. Okay, but if that's all the questions, guys online? Yes.
Are you going to do the Zoom thing in person?
You know what? If I'll start up a Zoom meeting. And so if you want to present via a Zoom, that will be fine. Yeah, if you want to present
Wait, no,
on
no.
Tuesday,
Does that also count towards?
that'll count. I'll count it.
So I don't have to like.
You don't even have to come into the classroom if you don't want to.
Yeah, that might do that.
Go for it.
Would it
I
be
won't-
cool if I set up a green screen now?
Wait, so when is presentations due again?
Tuesday the 13th at 2:45.
If it was Friday the 13th, I'd be terrified.
Mm,
Wait, so Society's due on Tuesday?
the slides, half a second, I hit the wrong button on my thing. The slides are due this Friday. Yeah. Yeah, so I'm grading your slides separately from your presentation. So just turn in your slides so I can grade them. Your presentations. Yes.
So if your slides have a lot of verbal content, should we add like extra slides saying, oh, say this verbally? Since the slides don't capture which one to say verbally when you submit it.
As long as you have like images on your slides, if your slides are just empty, that'll be a problem. But if you have like images and bullet points, but not like text, that'll be fine.
And the classroom is on this room next to.
This room, 2:45 Tuesday. If you're not here at 2:45, I'll open up the Zoom meeting, but if you're not there either, I'm leaving. That's my last class today. I'm not going to stick around waiting for people to show up. Okay, any other questions?
Nah,
Shall we talk about electromagnetic waves?
please. I need this for my slides.
Electromagnetic waves. Okay. So good. So this is the point of the whole class. This is what you should be here for. And so let's talk about how you get here. We started with electrostatics, which meant we had electric charges that stayed put. When the electric charge stayed put, what it did was make an electric field. So that was electrostatics. Then we had the charge move. So we had our point charge and it moved. And what we found was, I mean, I don't know if we found that it still had this electric field out, but it did. But really what we found that it made a magnetic field. So we had this electric field, but then also when it moved, it made a magnetic field in a loop. Let me see if I can make it loop correctly. Like this, where you put your right thumb in the direction of the velocity, curled your finger, and you see this magnetic field. Note that my electric field and my magnetic field are perpendicular to each other. Okay, that was electrodynamics. The electric charge was moving. Thank you. Sorry, I'm like restraining my mom urge to yell at the noisy kids.
Are they like visiting or something?
Oh, they are children. Okay.
Yeah, I see the whole lot of high schools.
Right. Okay, children. Okay. That's better. That's better.
Who screams at a kid?
Hi.
I'm sorry.
That's okay. I appreciate it. Okay. But now here's where the fanciness is going to come. We are now not only going to have an electric charge moving, we are going to have it accelerating. Because you probably didn't notice, but all through those magnetic fields that we were talking about, everything was moving at a constant velocity. You might say it was constant speed, but it wasn't speeding up or slowing down. Whereas here, now we're going to accelerate. And when we accelerate, what's going to happen is we're still going to have our electric field, but now our magnetic field, when it's moving slow, will be small. But as our speed increases, our magnetic field is going to increase as well. And this is going to do something weird to us, because through Faraday's law, the amount of magnetic field through a space that's changing with respect to time generates a voltage. Okay, so this is the weird part. We have our electric charge. It moves, that makes a magnetic field. But when it's accelerating, that magnetic field is changing. So that means that we have a changing magnetic flux through an area, and the changing magnetic flux generates an electric field, because that's what a voltage is. And so we have this cycle where if you start with an accelerating particle, charged particle, that makes a magnetic field that changes. That's going to cause an electric field that again is changing as this flux changes. That's going to circle back around and make this magnetic field that changes. And now we have this loop where our magnetic field changes, generating an electric field. The electric field changes, generating a magnetic field. And now it's this self-propagating thing. Like we had to start it with our accelerating charge. But once we had that, the magnetic field created an electric field, created a magnetic field, and it propagates by itself. It is self-propagating. Does that make sense? Gosh, I hope so. That's kind of the big thing here. Okay, this is an electromagnetic wave. And so let's draw something that you might be a little more familiar with, which is an antenna, right? Where what an antenna does is it takes charge across these things and it just vibrates the charge back and forth. Like, you know, you've seen like the big metal antennas. What's going on is you're just, you're putting like an AC voltage across it that flips. And so the current flips, goes back and forth. That's an accelerating charge. So that accelerating charge puts off a magnetic field. Whoosh, kind of like that. That magnetic field, because it's changing through Faraday's law, produces a changing electric field. That changing electric field pushes the magnetic field. That magnetic field pushes the electric field. And so these fields push each other that direction, where you have all these electric fields and these magnetic fields, whoosh, yeah, pushing on each other. Does that make sense? And even once the charge stops oscillating, these fields will keep on going. Okay. Yeah, this is my terrible picture of it. If you look in the book or even the homework, there are better pictures of this. But yeah, so here I have the electric field going up and down, and I have the magnetic field going in and out. Make sense? There we go. Yeah. Yeah, so I have the electric field in the y direction, plus and minus y, and the magnetic field in the plus or minus z direction. Where this whole thing is propagating in the x direction. So this is the direction of propagation. Okay. Where one thing you can kind of notice about this, and we'll talk about it more. So not only is the electric field perpendicular to the magnetic field at any point, also at any point, the direction of the velocity is in the E cross B direction. Just so you know, you can't compare the magnitudes here. This equation is not like a magnitude sort of equation. It's just a direction equation. That's why I have little hats on anything. But notice, like for this first box here, my electric field is in the positive y direction. My magnetic field is in the positive z direction. Y cross z gives you the x direction. And if you go to the next one, my electric field is in the negative y direction. My magnetic field is in the negative z direction. So negative y cross negative z gives you positive x. negative y, negative z, positive x. So anytime you can cross the electric field with the magnetic field, you'll get the direction that it's moving in. That should be a hat. Okay, that's the mechanism. Let us move a little further into this by looking at Maxwell's laws. And so here's where we're going to start with the math. Have you guys heard of Maxwell's laws? I did. Okay, I said something. I should say Maxwell's equations. Okay. There are 4 equations that you can use to describe any phenomena in electromagnetics. So we've spent an entire semester, we've covered a whole lot of different formulas. These 4 formulas encapsulate the whole thing. However, before we start in on them, we need to discuss displacement current. Displacement current. Okay. So, and here's why, and we're gonna need it to write down the 4 Maxwell's equations, but let's talk about it for a second here. We need it in particular to modify Ampere's law, where you probably don't remember, because I generally don't remember. Ampere's law was the one that said if you had a wire with some current going through it, and you made a loop around that wire that you call ds, then the magnetic field dot ds integrated over the entire loop would equal mu naught times the current inside the loop. And so like you had a wire with current going through it like that. You made this loop where whatever passed through that loop was what we called I enclosed. And then you said, okay, well, I know there's going to be some sort of magnetic field that looks like that. And so you did a B dot ds, where this thing was your ds. Integrated the dot product of the magnetic field and this loop that we decided on over the entire thing, and set that equal to mu naught times the current that went through it. And it was very much like a Gauss's law sort of problem, where the goal here was really to find an equation for the magnetic field. And so we would cleverly set up situations where we can be like, well, I could figure out this B dot ds, set it equal to mu naught times I enclosed, and then solve for B. However, there is one situation where it doesn't quite work. And so let's talk about that one situation and what we can do to kind of patch up Ampere's law. Okay. So, I have a battery. And I'm going to attach that to a capacitor that's initially uncharged. Okay, so as soon as I flip this switch closed, current's gonna go through here. Charge is going to start building up on these plates, producing an electric field. And I would like to talk about how Ampere's law works with that. Sound okay? I hope so. So I'm going to make myself, so let's flip the switch. I'm going to make myself a loop. So here's my loop. This is S. Looking at this loop, there's 2 kind of films I can make. So you notice how I made like that blue film, and that's what the I went through. There's 2 films I can make. One is just like the standard going through there. And in that case, I'll write in red. That case, the I enclosed is whatever the current in the circuit is. So I have an I. But I can also make this weird bubble film like this. Like that. So that the bubble isn't the current's not going through the yellow bubble. The yellow bubble just hooks over inside the capacitor. Can we all visualize that? And for the yellow bubble, the I that is enclosed, that penetrates through its surface, is 0, because no actual charge is going through that capacitor. So there are no electrons moving through my yellow bubble, and so the I enclosed inside of that is 0. And so this is a problem, because this means if we go to Ampere's law, it's possible to get 2 different answers. And there's only one right answer, because we've all, hooked up a capacitor at this point in time. So there's one right answer for this question, and so we need to find it. And this is where displacement current is going to come in. Displacement current is the idea of this because as goes through the circuit, charge builds up on these plates. And as charge builds up on these plates, my electric field changes. And so if I want to talk about what's affecting my magnetic field in between those capacitor plates, it's not that the charge moving would be making a magnetic field, it's the fact that my electric field is increasing. Sound okay? Okay, so conceptually, that's what's going on. We're going to define a thing that we're going to call displacement current. Displacement current, where it is going to look really familiar. Really familiar, but not quite. So we're used to seeing something where the magnetic flux changes with respect to time, right? This is an electric flux, so it's slightly different. However, looking at this, let's try to break this down and see what it really is. So I have I've defined this thing like this. Now my electric flux, just E dot A, right? We've done electric flux before, E dot A. So let's plug that in. So electric flux, E dot A, sorry. Now, we can totally do a Gauss's law thing, where we say, well, this is charge enclosed over epsilon naught, Gauss's law. Okay, and so if we take the derivative of this dt, that is the time derivative of Q enclosed over epsilon naught. Epsilon naught, is that a constant or a variable? Constant. Okay, so we'll pull that outside. Now the charge that is enclosed in this yellow bubble, is that going to change, or is that going to stay the same as current goes through this system? As current goes through this circuit. Should change, okay? So I'm not going to say like how much it changes right now, but when we take this derivative, it's not going to be zero because that charge is increasing. So d dt of this charge enclosed. Okay. Now think back. If you take the derivative of charge with respect to time, what is that? Current? Did you say current? Let's say current. Yes, current. Because current is how, when charge moves with respect to time, that's what current is, right? Okay, so this is really like a 1 over epsilon naught times some sort of current. Okay, now notice, okay, so this thing right there. And so when we have this displacement current, we're just taking that, multiplying it by epsilon naught to get our dimensions correct. And that really is a current. I'd also encourage you to think back to the Faraday's Law chapter when we did that problem with the toroid, and we talked about how the electric field in that gap changed and how that created a magnetic field. That's exactly the same thing as we're doing here. That's the same idea. Okay, and so what we're going to do is we're going to say, okay, we had this Ampere's law right there, and it worked great until you hit some weird region where you might not have current moving, but you'd have electric field changing. And so we're going to, and we patch it up using this displacement current. So now our new Ampere's law, oh, nope, do that. Our new Ampere's law, we are saying B dot ds, that's going to stay. Mu naught I enclosed. Oh no. And then we're just going to add on mu naught times displacement current. And we're all going to, there we go. That's much better. Okay, good, good. Where you can kind of fuss with this a little bit and say mu naught I enclosed plus mu naught epsilon naught d flux dt. Sound okay? So now, like if you choose the bubble where I enclosed is 0, you get the other bubble. And this allows us to write down all of Maxwell's equations. So back to Maxwell. Late 1800s dude wrote down equations that combined electric and magnetic fields, making electromagnetism. Did I talk a little bit about the grand unified theory at the beginning of this semester? Where you all went to just make like one big interaction? Yeah, so before Maxwell, you had electricity and you had magnetism, but you didn't put them together. And so Maxwell's thing of like, hey, electricity and magnetism are kind of the same thing. That was like a huge contribution. And it kind of started this idea that maybe we should try to combine all of our forces into one big thing. And we're working on that.
Like, would that be obvious? Like, forces act on everything, like with everything effectively?
Well, so with electricity, like I can move an electric charge and I can create a magnetic field. So I can do something to electricity and I can make magnetism.
Oh, it's like this does this.
Is there a
Yeah.
diagram?
And so for like gravity, you would want to say, okay, what if I move an electric charge? Can I make a gravitational field? So far, the answer is no-ish.
Wait, you can do that. You can create a gravitational field.
You cannot.
Yeah,
You
but
cannot.
ish, like there's a possibility.
Well, it's okay. One, there is a possibility because always a possibility. There is a thing that they called gravitomagnetism, which really isn't magnetism, but it's the idea that when you have mass that spins, the space around it kind of catches on the mass and kind of torsions as well. So like, you know how you might think of the Earth as the bottom of this potential well? It spins. And so you not only have this potential well, you have a potential well that kind of spins a little bit too. It's very weak. They were able to detect, they launched a probe, Gravity Probe B, they launched it and it circled the Earth a few times. And they were able to see that maybe space kind of torsioned as well. And they called it gravitomagnetic because magnetism is all about loops. And so everyone got really excited because they were like, oh, it's rotating. Surely we're going to be able to shove magnetism in there somewhere. And it's only like a decade ago, so, you know, maybe they will.
So
Yes.
is there a diagram that goes with this?
Oh, for Gauss's law? With
No,
this equation?
Maxwell's law.
Google Gravity Probe B. You'll get better, you'll get great stuff.
Okie dokie.
Not hypothetically. That's what we would like to do. We cannot do it right now. There's no science right now that says we can do it. It's just we feel we ought to be able to.
What's that called? Possible energy.
The perpetual motion machines. Yes, I'm sure that, like, I'm sure if you did make electricity, you'd slow down the Earth's rotation.
Yeah.
But still, like, that's still very science fiction-y. Okay. It's very cool. It's a good scientific field to go into right now. Okay, what do we got? We got Maxwell's equations, we got Gauss's law. Okay, so that was the first one. That talked about just like electric fields and how stationary charges made electric fields. We have Gauss's law again, so this is the electric one. Gauss's law again, but now for magnetism. And we mentioned this just like really briefly, where we had this idea that for magnetism, if you took a magnet and you put a closed surface around it, since magnetic fields do loops, just as much magnetism would leave as would come back in. And so there, if you have your closed surface that you're integrating over, that should add up to 0. And so this kind of gives you an idea of how electric field, magnetic field should look. Because electric fields, it says that they can point out radially, because if you integrate over shape, you don't get 0. But with this magnetic field, it's kind of constraining itself to loops, because that's how, if you have a magnetic field and you put in a surface around it, that all the magnetic fields going through that surface would add up to 0. You have to have this condition that says anything that goes out is going to come back in. Does that make sense? Okay, so that's what Gauss's law tells you about magnetism. It says it should be all loopy. Then we have Faraday's law. That's not the shape I wanted. Okay, Faraday's law, E dot ds equals negative d phi b dt. And kind of note that E dot ds, this is an electric field over a space, so this is really a voltage. So anytime you have an electric field extended over a space, what you get is a voltage. And so this is Faraday's law, where a changing magnetic flux gives you an electric field. And then of course Ampere's law, what we just went over, the B dot ds. Mu naught I enclosed plus epsilon naught mu naught E d phi dt. Ampere's law. Okay. Okay, this looks good. So a few things here. The first two, Gauss's law, time independent, right? That's for stationary stuff. It's not changing with respect to time. The next two, very time dependent. So the magnetic field, the electric fields, they're changing with respect to time. And so they're talking about how if magnetic fields change with respect to time, how does that make an electric field? If an electric field changes with respect to time, how does that make a magnetic field? Sound okay? Okay. Now, we are doing electromagnetic waves. And here's the thing with electromagnetic waves. They can exist in a vacuum. Can other waves exist in a vacuum? I don't think so at all, right? Because in fact, you define other waves by what medium they're moving through, right? Like, yeah, you need air. Water waves, you need water. So in general, when you think about waves, what you're thinking about is energy and momentum moving through a medium. Like when I talk, my vocal cords push on air, that pushes on the next bit of air, that pushes on the next bit of air, and it makes this continual motion until it reaches your ears. But without the air, you would not be able to hear me because there would be nothing for my vocal cords to push on. EM waves are extremely unique because they can exist in a vacuum. We know this because we can see the sun, and it's out in the vacuum of space. So you can't hear it, but you can absolutely see it. Okay. And this is actually a big deal. Before certain theories existed, there's actually this theory that the universe actually had this ether that was kind of like a soup that we all kind of lived in, and that's how light got from one place to another. Is it propagated through that ether? We decided there's some experiments done, and that was decided that probably wasn't true. But it definitely was like a conflict that you had to think about. So let's take Maxwell's laws and let's put them in a space where there is nothing. So for example, Gauss's law, E dot dA equals charge enclosed over epsilon naught. For in a space there is nothing, that means there can't be charges. Make sense? So in a vacuum, that would be zero. Gauss's law for magnetism, you get nothing that interesting. It's still zero. But then we hit the second two, the Faraday's law and the Ampere's law, where if you're in a space where there's nothing, no medium, no physical quantity that you can hold on to, you can still have fields. So fields still exist. So even without a charge there, you can still have this electric magnetic field interaction. And same with Ampere's law. You lose this I enclosed bit because if you have an actual current that's charged, and we're saying there's no charge, but you can still have that electric field. And so this is what we're going to build our electromagnetic waves out of. We're going to build them out of this idea that even in a place where there's no particle, this part of the interaction can still exist. Yeah.
So would it still exist like a black hole?
Yes, it would. Black holes are not vacuums, though. They are matter. Yeah. The idea is the black hole is it's a well it's a singularity where there's so much gravity that it affects things in an extreme way, and we assume that that gravity probably comes from matter. I don't think you can't. Problem with black holes is you can't get inside them and look out. It's a one-way sort of trip.
I thought, like, doesn't it suck things up? It's there. That's what I thought. Well, we say vacuum, you need just no air. Is that what you mean?
So by vacuum, I mean both no air, but also no anything else. Like no suns, no planets, no charge, no nothing.
Parts of space are vacuums, but like when you're at the sun, since you're at the sun, even if it's in space, it's not a.
Yeah, so I have this sun over here, and I have the Earth over here. Sun's not a vacuum, the Earth's not a vacuum, but everything in between it is a vacuum. So yeah, the whole thing of space is it's empty. Like it doesn't have wind, it doesn't have dust, it's just empty. I forget what I was talking about. No, that's okay. It's really easy. Right. Okay. Yeah. So we have these two equations, and we want to make an electromagnetic wave. All right, we can do that. Let's make some waves. Okay, so conceptually, we understand. I'm going to draw this picture again, and it's going to be terrible. We understand that we have an electric field going that way, and that pushes this magnetic field while this whole thing propagates in that direction. Going to give myself a coordinate system to work with. X, Y, Z. Okay. Whoosh. There's my electric field. Along the y-axis, there's my magnetic field. Along the z-axis, the velocity goes this way. That's the direction of propagation. What I would like to do is I would like to find an equation where at any point in both time and space, that sounds fancier than it really is, but if I want to say that point in space and 10 seconds into time, I can tell you what the electric and magnetic field are right there. Sound okay? So I want an equation of the electric field with respect to time and space, and the magnetic field with respect to time and space. Okay. Okay. Let us start right here, where we're taking my electric field, integrating it over a loop, and that is how my magnetic field through that space changes. Okay. And in particular, let's look right here, where my electric field does this, and my magnetic field comes out like this. So my electric field is up, and my magnetic field is in the positive z direction. Okay. This says integrate the electric field around a loop. E dot ds, integrate around a loop. So first thing we need to do is we need to make a loop. We're going to make a loop that's very convenient to us. It's going to be a rectangle. where the rectangle has length dx and height L. Okay. Whoosh, whoosh, and we're going to go around it in that direction. I like it. Okay, so where should I put this? Okay, E dot ds equals sorry, I don't have this well mapped out. I have 1, 2, 3, 4, my 4 sides. So side 1, I have the integral of the electric field dot dx. Sound good? Okay. Side 2, I have the integral of the electric field dot L. Let me write that differently. Dot ds from 0 to L. That's better. Next one. 2. Okay, again, I have the electric field dot dx, but my dx is now in the negative direction. And last one, electric field dot ds, and now I'm going from L back to 0. Is that all good? So I just went around my rectangle. Okay, and if that's good, my electric field is in the y direction. My dx is in the x direction. When I take the dot product of these two vectors, what am I going to get? And when you take, are these two vectors parallel or perpendicular? Perpendicular. Dot products takes what's parallel between two vectors, right? So when you take the dot product of two vectors that are perpendicular, you get 0. Does that make sense? Okay, this guy is 0. This is 2, this is 3, this is 4. What can you tell me about the third integral, E dot negative dx? What's that dot product going to give you?
0 again.
Would be 0 again. Okay, this is looking good. Now, here's what's going to get a little bit weird. When we do 2, this will be the electric field at 2, and we do 4, let's call it the electric field at 4. Where those electric fields might be slightly different because one's a little ahead of the other. So if you think of this electric field, what's happening is it's going up and then going down like that, right? So if it's going up, whatever the electric field is here, it'll be here a second later. Make sense? So if I want to combine these things, if I want to relate these things, I would say the electric field at whatever spot plus dx. So this would be like the electric field at 2. That'll equal the electric field at point x, and so that's the electric field at point 1, plus whatever the electric field has changed over that space. Holding time constant. Does that kind of make sense? And that doesn't even tell you much about this. All that tells you is that my electric field at this point is the electric field here plus whatever it changed. We could say that about anything, right? The electric field here plus what it changed, that's the electric field then. Okay, but now we're going to take this and we're going to plug it in here. We're going to take, do I need to take this? Oh, no, okay, I'm sorry. My bad. We're going to take this and we're going to plug it in here. That's where that goes. And we're going to just take this and we're going to plug that in there. That's much better. Okay, let's do that. Okay, so we're still looping around our e.ds. We've gotten rid of 2 of the sides. The other 2 sides we have are the integral of e of x, no plus, yes plus, yes plus, plus partial e with respect to x, ds from 0 to L, and then we do this other one, plus e of x ds from L to 0. So far, so good. Okay. I'm going to take this first integral and I'm going to split it up because you can always split these things up. ds 0 to L, partial e, partial x, ds. And then this third one, we're going to do something fancy with. Notice for the first integral, we're going from 0 up to L. And then for the second integral, we're going L down to 0. So we flipped our limits. And I'm going to flip them and multiply by -1. Because what we're really doing is we're doing this integral and then we're going to take the 0 minus L. And so if instead we took the L minus 0, we just multiplied by -1 there. So I'm putting a minus sign right there. 0 to L, e of x ds. And now you're going to tell me what cancels.
First one. Oh, sorry, the first and the last.
Yeah, the first and the last. Okay. So we had something kind of complicated, and now it's going to come down to kind of something straightforward. We're integrating around this e.ds. We found that really that just is this 0 to L of partial e partial x ds. And we can even kind of take this a bit further. If I can find my pages so I get it right the first time. Nope. It's really fun for you guys. It'll be really fun for you guys. You can take this and you can integrate with respect to ds. You can say this is partial e partial x from 0 to L ds. And when you integrate ds from 0 to L, you just get L. Okay. Okay, so I have e.ds equals partial e partial x dx times L. Did I do that right? Yes, I did. Let me put my loops in the right place. And let me say that is a lot. And that this equals negative d phi b dt. Okay. Now, here's where I feel I'm just gonna start skipping steps because I don't know if I'm doing this any better. The steps I'm gonna kind of like skip around here is you do the same thing to the magnetic part. You do, you say your magnetic field looks like this. You make yourself a loop like that. And you go through B dot ds equals epsilon naught mu naught d phi e dt. Okay, cool. But this way, what you're doing is you're combining your electric and your magnetic field. And so you go through that and you end up with a really reasonable thing that looks just the same. Dx equals epsilon naught mu naught d phi e dt. Okay, and so now that you have the same thing on both sides, what you really have from this is you really have negative O partial B partial X dx equals this guy, which is a bunch of constants, times the electric field dot A with the derivative there. And I'm kind of, and from what you should see there is now we have this thing right here where the area dx times L, sorry, catching up, dx times L equals this over here, L partial B partial X dx. Those things cancel out. And what I very clumsily have gotten to finally is this equation, where this was really the important part all along. Sorry that took so long. Okay. So here's the big thing. This is why this is important. This tells you how the magnetic fields and the electric fields are related through space and time. And if you do a lot, and so whatever my electric field does, if you take the time derivative of it, that needs to be what my magnetic field is doing with respect to space. And where did I put my other thing? And that's the same thing with electric field. You have this electric field derivative with respect to space. You have this magnetic field derivative with respect to time. Is that kind of okay? Okay. Let me tell you, you combine that equation, and I really am going to skip it this time. That equation, these two equations, this guy and this guy, and you can end up one of two places. You can end up here, or you can end up the same place, but with electric fields. Partial E squared, partial X squared, just depending on which way you decide, whether you're taking the substituting in your electric fields into your magnetic fields, or your magnetic fields into your electric fields. Okay, overly complicated, but this is where we need to be. This sometimes called the wave equation. I'm hoping you're looking at it and you're saying that's a differential equation. And that's what is going to dictate what our electric and magnetic fields should look like. Yeah, that's where it was. Great. So let's do this the physicist way. And let me ask you, what this says is I have an equation that I'll take the second derivative of one way, and I'll take a second derivative the other way, and I need to get back to where I started. What functions do you get if you take two derivatives of it, you get back to where you started?
You said it again?
If you take what derivatives, if you take two derivatives of them, what functions, if you take two derivatives of them, you get back to where you started?
Oh, integrals?
Give me like a x squared, sine, cosine, exponential, logarithm. Sine and cosine are good because if you take the derivative of sine, you get a cosine, derivative of cosine, you're back to a sine, right? Sine and cosine work. Exponentials work as well because, yeah, like anytime you take the derivative of an exponential, you just get back the same thing. Yeah. So those both of those work pretty well, which is why sines and cosines and exponentials are actually kind of the same thing. This particular book chooses to use cosine. So we are going to start with just a guess where we are going to do a few things here. So we have a cosine. There needs to be a cosine in there. So we have a cosine wave. We put an x and a t in there because I know it's both a function of x and t, and I'm going to multiply them both by a constant because they're probably going to be multiplied by a constant. And I'm carefully choosing my letters because I know the answer, but we'll figure out what those letters are in a second. I have an E max multiplying the cosine because I know there's going to be a maximum value, so that's the amplitude of my wave. And the minus sign is another well-considered. I know that a minus sign needs to show up, so I have a minus sign in there. Okay, let us verify that this works, and by that means we took a guess. We're going to plug it into this equation, and if we take two derivatives with respect to x, and then two derivatives with respect to t, and we can set the two sides equal to each other with a couple of constants here and there, then that means that we got a good answer. Does that make sense? Okay. Let me say that of course you could, like if we put in signs, that would work as well. And so your differential equation can definitely have more than one answer. Okay. So let's take this derivative. E max, the amplitude of a wave. Would you consider that a constant or a variable? Constant. Excellent. Derivative of cosine? Sine. Is it negative or positive? I think it's -2. Okay. So we'll throw a minus sign out front. And we're taking this derivative with respect to x. So we need to take the derivative of the inside. So what's the derivative of the inside with respect to x?
Just R?
Yeah, that's a k, by the way, but that's fine. But yeah, that thing over there, let's call it k. That's okay. It's italic. Okay, that's great. Let's take the second derivative of this thing. So the second derivative of e with respect to x is the derivative of this. You guys have already told me that E max is a constant, so we'll pull that out. That k is also a constant, so we'll pull that out as well. I'll pull that minus sign out, so I have k E max. Okay, and then we're taking the derivative of sine. What is the derivative of sine? Cosine. And we need to take the derivative of the inside again, and the inside hasn't changed, so we actually have two of those. Okay, so this is partial e squared, partial x squared. Okay, let's circle that and do the other half of this equation. So now let's take two derivatives with respect to time. Okay, the partial derivative of e with respect to time, partial t e max cosine kx minus omega t. Okay, e max constant. Derivative of sine, cosine, negative sine. But now take the derivative of this inside with respect to time instead of space. Negative omega. Okay, this looks good. Those minus signs cancel, but everything else looks great. Taking a second derivative, partial t of this whole thing, e omega, the sine e max omega sine kx minus omega t. Whoosh. Okay. Constant. Derivative of sine, cosine, and derivative of the inside, negative omega. Okay, now, okay, so this is partial squared e with respect to t. Circle that up. Now we put both of these into our overall equation. So on one side, I have negative e k squared cosine kx minus omega t. On the other side, I have negative mu naught epsilon naught. And my list. That is negative E max omega squared cosine kx minus omega t. Sorry, I kind of ran out of space there. Which is okay, because what are we going to do with that cosine? Looking at this equation, we can just cancel it, right? Okay, and so that right there is what tells us that this equation does satisfy our differential equation, because that means that the variables on either side always are going to match up. All we have to do is look at the constants now. Where let's look at these constants. Where I swear I've lost a minus sign. This is like the third time this day I've lost minus signs. Our Emaxes go away. That's great. That's not a problem. That's in fact what should happen. And then we have epsilon naughts.
Wait, would it go away? Would the Emax on the right be positive since it's multiplied by the negative?
So I can cancel them out, but yeah, I do need to look at those minus signs, which I feel this minus sign right here should never have been there, which makes this even better. That minus sign shouldn't have to be there, but now what's happening to my minus signs? Yeah, sorry, no minus signs. Perfect. Okay, now here's the fancy part. Here's the part where it's all going to come together. I'm going to move my k squared to this side. I'm going to move my mu naught epsilon naught to the other side. And I'm going to say something about what these omega and K's are. Where omega 2 pi f, right? It's, yeah, it tells you how quickly your frequency, your wave is flipping up and down. Okay, K is actually called a wave number. It fulfills the same purpose as the angular frequency. It is 2 pi over the wavelength. And so it tells you how many wavelengths fit into 2 pi radians. Does that make sense? So it does for the length what omega does for the time.
It would just end up being frequency times level.
Excellent question. Okay, so if you do, so if you do a omega over k, that's 2 pi f over 2 pi over lambda. Okay, so yeah, your 2 pi's are leaving. And so you have frequency times wavelength. Do you guys know what that is? Okay. Let me tell, I have to wrap this up because I'm out of time, but here's where we're going to start on Thursday. That's actually going to be the speed of light.
Specifically for light.
Not specifically for light, that's actually a really good point. This is going to be the speed of any wave. Since we're talking about frequency and wavelength of light, we're going to end up at light. But please remind me, this is where I want to start off because I want to say why frequency times wavelength will end you up with the speed. Sound okay? Do a unit analysis when you get home and you'll be where you need to be. But yeah, we'll start that. We'll get the speed of light in a vacuum. We'll talk about how that relates to this week's lab, which by the way is amazing. And we'll go over any final due dates. Any questions?
Will we still have access to XPGA even after 2?
I think I set it to be like end of December or something. If you need to download something, definitely do it like by the end of next week or two. Because I don't remember exactly what I set it to.